pass to you.
Can I stand here?
Oh, hello. Today's topic is picture file sizes.
All right, so let's talk about the next topic. Hopefully everyone can see my iPad here. This has got the same text that you've got in your textbook that I gave you. This where we're going to be working on mostly from today's lesson, because there's some really good diagrams and pictures in here that we talked about. That we're going to be talking about. So a really important topic we're going to be looking at is how to calculate image file sizes. We've talked about how chars and integers and floating point numbers and all sorts of things like that are stored in binary, how it turns zeros and ones. But of course, if you're looking at a computer screen right now, like you are doing, you're not just seeing zeros and ones. You're not just seeing numbers and letters. You're seeing colors, pictures, all sorts of things. So there's a lot of other stuff your computer is doing using zeros and ones that isn't just floating point numbers and binary representation and videos and and other things like that. So we can sort of get to videos here as well, but we'll start with photos. It's just really simple registration of how, using only zeros and ones, your computer can store pictures. So the most important concept so far is talking about bit depth. I'm going to make some annotations on this document. I hope you can see when I draw a circle around that bit depth title, because when we're talking about bit depth, we're essentially talking about how many bits are used per pixel. That's the most important thing. Let's have a look at this picture right here. This is a picture of the Mona Lisa, a part of the Mona Lisa, and you might think that that looks like it's a traditional black and white image where we've got blacks and whites and greys. But if we zoom in on that picture and zoom in even further, we can actually tell that this is not just a grayscale picture, or there's no actual greys there. Every single pixel is black or it's white. That's a really important idea to get through, that we've got pixels there that are either black or white, and thus every pixel is on or off. We can essentially store that as a grid that looks like, well, our top left corner pixel is on, and then we've got two that are off, and then one that's on, and then a few that are off, and then we've got we can really store that as just a series of bits that look like this, where every pixel where every 0 or 1 corresponds to a pixel in the top left corner of this image. So we're really just storing zeros and ones. This particular picture has a bit depth of 1, as in we are using 1 bit for every pixel. And if we zoom out and you make your resolution small enough, you can create the impression that you've got a black and white image. So I am recording the video and you can watch it all back later. All right, so we've got a bit depth of 1 in something like this. Let's have a look at this picture here now, which is another picture of the Mona Lisa. Here we can see, and maybe you can zoom in on your screen, have a good look at the picture. We've got a bunch of different pixels here. Like just here, for example, on the bridge of her nose, we can see that there is one. I'll just undo that so you can see it clearly. There is one pixel that might be a different color. We're actually using several different colors of pixel here. Everything is either that light brown color, or that medium brown color, or that dark brown color, or that nearly black color. So we've got 4 different colors there, and every single one of those pixels is one of those colors. How many bits do we need to store 4 colors? Well, we know that if we're going to have 4 different colors, like maybe light brown and medium brown and dark brown and black, then 0, 0, 0, 1, 1, 1, 0, 1, 1. We can give each of those pixels a 2-bit code. So to store 4 colors, we only need 2 pixels. That means we're going to need 2 different bits for each pixel. So if we think about how this picture might be stored compared to what was happening up here, now I'll just change color so I can draw over myself without too much difficulty. Now we're going to have something that, instead of having 1 bit per pixel, we're going to have to store, well, this one up here looks like it's 0, 0. And then the next one is going to be 0, 0, and then we've got a pixel that is our darker brown, which is 0, 1, and 0, 0, 0, 0, 0, 1. So we're now using 2 bits per pixel. So this picture here has a bit depth of 2. By increasing the bit depth, that's a 4-color system. You might think that's pretty old and obsolete, but 4-color systems were around, certainly when I was growing up. Here's some examples of some games. This is a classic game called Prince of Persia, and it's games and real computer graphics that use 4 bits. This particular system is something called the CGA system. Oops, CGA. You don't have to know about the CGA system apart from that it's a 4-color system. If you do a Google search for CGA computer graphics, you'll see a few interesting pictures of lots of games that look sort of like this, that use only 4 colors. You'll also notice, if we compare these 2 images, let's compare sort of this Prince of Persia image to our Mona Lisa image. You can see that with the Mona Lisa, we've got 4 colors that we sort of can choose what we want. So in this case, when creating the Mona Lisa, the computer's determined that representing this as 4 different colors, the best colors will be this light brown and this medium brown and this dark brown and this black. And so we've customized those colors. We've picked which 4 colors we want. If we're using something predetermined like the CGA system, the CGA says you can use this aqua and this magenta and a black and a white, and they're the only colors you can use. So you don't have any choice about which your 4 colors are. The easiest way to think about that is that this system here is something called a color lookup table. If you see the word color lookup table, it just means that we can look any colors up. We're only allowed, if we've got a 4-color lookup table, we're only allowed to use 4 colors total, but those 4 can be anything that we want. As opposed to a predetermined system like CGA, where we are also limited to 4 colors, but here they're not 4 of any colors, they're 4 very specific colors. That's going to come into it a little bit later. You need to know the difference between a 4-color lookup table or a 4-color predetermined. All right, now let's get on to our current. This picture here actually is corresponding to the previous page. You'll notice, one thing you might not notice with these is that every single picture, no, that's not quite true, not on the one I'm looking for, never mind. So here we've essentially got different pictures for the Mona Lisa where each one has more color depth. And so this one here, we're limited. You can certainly see the pixelization around her nose and around her face. That seems to be not showing up on my screen that I'm looking at. I hope I haven't broken it. Sorry. All right. So if we're looking at these, yeah, now it's working. All right, so if we're looking at these pictures of the Mona Lisa going from left to right, all we're really doing is increasing the color depth there. They might look the same, but when you get closer, you can see that, okay, one of them has a grainier looking pixels, and that's just because we're using fewer bits to store our pixel color, our color information. And if we're using fewer bits to store our color information, then we're not allowed as many colors. And so the differences between adjacent colors are more glaring. That's a bit of the history of the stuff, but now pretty much every computer laptop that you're looking at, every document, every picture uses 24-bit color. It's the same color we've looked at earlier, so let's talk about it. Most modern computers and devices use 24-bit color depth because it allocates 24 bits per pixel. So 24 might seem a strange number. It's not a power of 2. It's not one we've looked at in the past. We know from our binary that units, 1s, 2s, 4s, 8s, 16, 32, are all really common usage because we can count up with binary, and each one of those is a new one. Why 24? It's not a power of 2. Well, the simple fact is that 8 is a really common value. Indeed, sorry, we're not going to use 8 because we can count up to 8 using only those bits. Units, 1s, 2s, 4s gives us 8 values. And so if we have that amount for our red and our green and our blue channel, we've got 4 bits, sorry. We've got 8 bits for our red, 8 bits for our green, 8 bits for our blue, and that's going to give us, sorry, that should go further because we do go up to 32. And so that gives us, no, we go up to 64, never mind. So essentially if we give 8 bits, so green might be 0, 0, 0, 0, 1, 1, 1, 1, and blue might be 0, 1, 1, 1, 0, 0, 0, 0, and red might be 0, 0, 0, 0, 0, 0, 0, 0. So we're allocating 8 bits for our red channel, 8 bits for our green channel, 8 bits for our blue channel, and that gives us 24 bits total. Now let's look at this color here. An R value of 0, 0. We can also just write that in hexadecimal as 0, 0. Our blue channel here, we've got, remember when we're doing hexadecimal, we just divide it into 4 bits at a time. And so in this case, 0, 1, 1, 1 converts to the decimal value of 7, hexadecimal of 7, 0. Oh, sorry, except I'm doing red, green, and blue. So I did those in the wrong order. So that's our red value as hexadecimal. Our green value is going to be 0F, and our blue value is going to be 07. No, 70. My apologies, 70. This is a shorthand way of writing our color. We could write this in Java as, let's create a new color that is 0, F is 15, 7, 0, 7 times 16. What's 7 times 16? 112. So we could write this as this color, which is going to be a fairly dark blue. Or we could also write it in hexadecimal looking like this. And if we do write it in hexadecimal looking like this, we often put a hashtag in front of it like that. So it's another representation of our 256, sorry, not 256, of our 24-bit color system that we've been using right since day one when we were doing things in Java and writing hello world and declaring colors. And we often take a number that looks like that and we can write it like that as well. So I'm sure if you've done any multimedia or any other digital graphic production, you've seen colors written like that. Essentially now we know why. What's actually happening is that we're taking our color in this sort of system, our 0, 15, 112 RGB values, and turning each one into a hexadecimal value, which we already know how to do thanks to your work last week, and we can write it using that new system. So this is the main system that we work with. It's a bit depth of 24. Now, remember, our original topic we were looking at was how can we work out the file size? If we have a picture, can we work out what size our picture is going to be in terms of bits? And it's pretty simple because if we know how many pixels there are in our picture, then we just have to multiply that by the bit depth. Let's have a look at this picture. Let's say that we've got a picture that is 640 pixels wide, 480 pixels high. And how many colors are there in this particular picture? There is 1, the black. There is 2, that is that blue color. There is 3, that is the green. There is 4, that is the house color. So we've got 4 different colors in this. That door, you'll notice, is the same as the sky, so we don't have to count that as well. So we've got 4 different colors. That means we're going to need 2 bits to store this information. It's got a bit depth of 2. And thus, to work out our size, we simply multiply our height by our width to work out how many pixels there are total, and then multiply that by, there's a typo there, that should say 2, and then multiply that by 2 to get that many bits, which we can then convert into kibibytes as discussed in our previous topic as well. So we can work out how big, in theory, pictures will be on our hard drive. However, that's a little bit of an oversimplification, because remember how this picture has 4 colors that look like they've been decided to be the best. How do we keep track of the fact that color 1 is black and color 2 is a bluish color and color 3 is that greenish color and color 4 is the reddish color of the house? Well, if we're storing this picture as a 2-bit depth picture, we're also going to need to store the information about what colors those are, and that information is stored in the color lookup table. It also gets called a CLUT. And so in this case, what we actually would need to do is something that would say, okay, if we get a pixel combination of 0, 0, that's color 1, which is going to be black I'm going to store that as the hexadecimal color 00000. And color 2 is going to be my blue one. That's a nice light blue. So let's make it something like 000. No, hang on. This color would be something like, let's say 7777FF. That's going to be a nice blue color. Green 10 is going to be our 77FF77. I'm just guessing what these colors might be, but as long as I'm picking a reddish and a bluish and a reddish, no, a greenish, and then color 11. That's going to be my red color. Let's just make it 770000. All right, so essentially we need to store these 75 kibibytes, which is what our 307,000 pixels are doing. That's storing this information. That's storing for each pixel, is it a 00 or a 01 or a 10 or a 11 for each of our 307,200 pixels. And then we also need somewhere this information stored just once. We don't need to store that 307,000 times, but we just need to store somewhere in our same picture. Okay, well, if we see this pixel combination 00, that's actually referring to here. It's called a color lookup table because it's exactly what we're doing. We're looking up our color each time. Now, usually a color lookup table will be assuming that what's stored here are the 24-bit colors. So in terms of our total file size, this is going to be our 75 kibibytes plus our 4 times 24-bit. We usually say that it stores this bit of information as well, this bit on the left, but we don't actually need to. But if we're adding up how many bits, we've got 614,000 bits plus 4 times 24, which is 96. Plus, if we really want to store our references, there's another 8. You can see that in the grand scheme of things, this 614,000 bits of what our pixels are storing, and this 104 is what our color lookup table is storing. So that's why the color lookup table makes up a very small amount of the total picture, but we do need to still consider it in most test questions. That's sort of the key points. There's a little bit more here that you can read that I'm not gonna go through, but I'd suggest you read up. I mean, there's more information here on a color lookup table. That's an example. What I've just done is gone through an example of a 4-color lookup table. But here is a discussion about a 16-color lookup table. On the left here, we've got an image using the 16 colors that are predefined in the EGA color palette. And here we've got still using only 16 colors. We've got exactly the same picture. It's still using 16 colors. The difference is that these are 16 adaptive colors. That keyword adaptive basically means we're looking it up on a color lookup table. And so there's another example there of going through a color lookup table in a more complex situation. I'm not going to worry about it too much, but you can read through that. Now, there are some questions for understanding here that I want you to have a crack at.